Welcome back to Whispering Universes, where we trace the ancient paths of wanderers through the cosmic dark, following light across billions of years to understand the silent stories written in ice and dust. Tonight, we turn our attention to some of the most enigmatic and beautiful travelers in our solar system: comets. These frozen visitors from the outer darkness have captivated human imagination for thousands of years, appearing suddenly in our skies with their glowing heads and streaming tails, seeming to defy the orderly procession of stars and planets. Unlike the predictable motions of our moon or the steady circuit of Jupiter, comets arrive unannounced, blaze across our view for weeks or months, and then vanish back into the void, sometimes never to return. For most of human history, comets were seen as omens, harbingers of disaster or divine messages written in fire across the night. The appearance of a great comet coincided with wars, deaths of kings, plagues, and upheavals. No one understood what they were or where they came from. They seemed to violate the celestial order, moving through space in ways that defied explanation. It wasn't until the scientific revolution that we began to understand comets as natural phenomena, following the same physical laws as everything else in the cosmos. And what we've learned is more extraordinary than any ancient myth. Comets are time capsules, frozen remnants from the very formation of our solar system, 4.5 billion years ago. They contain pristine samples of the material that formed the planets, preserved in deep freeze at the outer edges of the sun's influence. When a comet falls inward and approaches our star, solar heating transforms it, releasing gases and dust that create the spectacular tails we observe from Earth. These tails can stretch for millions of kilometers, catching sunlight and glowing against the darkness. They're among the largest structures in the solar system, yet they're made of material so tenuous that if you could gather all the substance in a comet's tail, it would barely fill a swimming pool. The story of comets connects to fundamental questions about our origins. Did comets deliver water to Earth's surface during the planet's formation? Did they bring organic molecules, the chemical building blocks of life? Are comets responsible for seeding worlds with the ingredients needed for biology? These questions remain partially unanswered, but we're learning more with each passing year. Spacecraft have visited comets, touched their surfaces, analyzed their composition, and returned with data that's revolutionizing our understanding of the early solar system. As you settle into this exploration, imagine standing on Earth 4 billion years ago, when the planet was young and the bombardment from space was still intense. The sky would have been filled with comets and asteroids, their impacts delivering water and organic compounds to a world that was beginning its long journey toward hosting life. Each comet represented a piece of the original material from which the solar system formed, arriving like a messenger from the ancient past. That bombardment eventually subsided as the planets cleared their orbits, but comets continue to visit, falling in from the distant reaches where they've waited in frozen darkness since the beginning. Here on Whispering Universes, we'll trace the complete story of these frozen wanderers. We'll explore where comets come from, what they're made of, why they develop their spectacular tails, and what they tell us about the formation and evolution of planetary systems. We'll examine specific comets that have captivated observers throughout history, from ancient appearances recorded on clay tablets to the spacecraft missions of the 21st century. We'll consider the physics of sublimation and the solar wind, the chemistry of ices and organics, and the dynamics of orbital mechanics that bring comets into our view. And we'll reflect on what comets mean for understanding our place in a universe that preserves its history in frozen archives scattered across billions of kilometers. Let the boundaries between ancient and modern begin to dissolve. Let your mind drift outward to the cold regions where comets wait. And let's begin this journey through time, following frozen travelers as they fall toward the light. 4.5 billion years ago, our solar system didn't exist. In its place was a vast cloud of gas and dust, a molecular cloud drifting through the spiral arm of a young Milky Way galaxy. This cloud was mostly hydrogen and helium, the primordial elements formed in the Big Bang, but it also contained heavier elements: carbon, oxygen, nitrogen, silicon, iron. These had been forged in the cores of previous generations of stars and scattered into space when those stars died in supernova explosions. The cloud was cold, just a few degrees above absolute zero, and its density was incredibly low. You could travel for kilometers through it and barely encounter any atoms. Yet the cloud was immense, spanning light years, and its total mass was substantial. Gravity began to pull the cloud together, perhaps triggered by the shockwave from a nearby supernova, or by the gravitational perturbation of passing stars. The cloud started to collapse. As it contracted, it began to spin, and conservation of angular momentum caused it to flatten into a disk. At the center, where most of the mass concentrated, temperatures and pressures rose until nuclear fusion ignited, and our sun was born. But in the disk surrounding the young star, in the protoplanetary disk, the material remained relatively cool. Close to the sun, temperatures were high enough that only rocky materials and metals could condense into solid form. This region became the inner solar system, where Mercury, Venus, Earth, and Mars would eventually form. Farther from the sun, beyond what's called the frost line at around 5 astronomical units, from our star, temperatures were low enough for water ice to condense. This made an enormous difference. Water is abundant in the universe, and once it could freeze into solid form, the amount of solid material available to build planets increased dramatically. This is why the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in the outer solar system. They had access to ices as well as rock and metal, allowing them to grow massive enough to capture thick atmospheres of hydrogen and helium directly from the nebula. But planet formation wasn't perfectly efficient. Not all the material in the protoplanetary disk got incorporated into planets. Small bodies, planetesimals ranging from meters to hundreds of kilometers across, continued to orbit the sun. In the inner solar system, these became asteroids. In the outer solar system, beyond Neptune's orbit, they remained as icy bodies, frozen mixtures of water ice, frozen carbon dioxide, frozen methane, and rocky material. These are comets, or more precisely, comet nuclei, the solid cores that would later develop tails when they approached the sun. The region beyond Neptune contains 2 vast reservoirs of comets. The first is the Kuiper Belt, extending from roughly 30 to 50 astronomical units from the sun. This is a relatively flat disk of icy bodies orbiting in the same plane as the planets. Pluto is the most famous object in the Kuiper Belt, though thousands of others have been discovered. The Kuiper Belt probably contains hundreds of thousands of objects larger than 100 kilometers across, and trillions of smaller bodies. These are short-period comets when they fall inward toward the sun, their orbits typically lasting less than 200 years. Even farther out lies the Oort cloud, a spherical shell of comets surrounding the entire solar system. The Oort cloud extends from roughly 2,000 astronomical units to perhaps 100,000 astronomical units, nearly halfway to the nearest star. At these distances, the sun appears merely as the brightest star in the sky, providing almost no heat. Temperatures are only a few degrees above absolute zero. The comets here move slowly in their orbits, taking millions of years to complete one circuit. The Oort cloud probably contains trillions of comets, representing a mass perhaps several times that of Earth. These are long-period comets when they fall inward, sometimes taking thousands or even millions of years to orbit the sun. The distinction between these reservoirs matters because it affects the comet's orbits and behavior. Kuiper Belt comets orbit roughly in the same plane as the planets, and they tend to return predictably. Halley's Comet, with its 76-year period, likely originated in the Kuiper Belt, though gravitational interactions with Jupiter have modified its orbit. Oort cloud comets, however, can come from any direction, plunging through the solar system at steep angles to the planetary plane. Some arrive moving so fast that they're not gravitationally bound to the Sun at all. After one pass through the inner solar system, they'll escape and never return. What perturbs these distant comets, sending them falling toward the inner solar system? For Kuiper Belt objects, gravitational interactions with Neptune gradually alter orbits over millions of years. Some objects get nudged into resonances with Neptune, orbital periods that are simple ratios like 2:1 or 3:2. These resonances can either stabilize orbits or destabilize them, depending on the specifics. Destabilized objects can be scattered inward, crossing the orbits of the giant planets, where further gravitational encounters can send them into the inner solar system. For Oort cloud comets, the perturbations come from different sources. Passing stars, even at distances of light years, can gravitationally disturb the outermost comets. The Milky Way's gravitational field, the combined pull of billions of stars, creates tidal forces that affect the Oort cloud. These galactic tides can gradually alter comet orbits over millions of years, occasionally sending a comet inward. Encounters with giant molecular clouds, vast regions of gas and dust between the stars, can also perturb cometary orbits. All these influences create a slow but steady rain of comets from the Oort cloud into the inner solar system. The total population of comets in both reservoirs is staggering. Estimates suggest the Kuiper Belt contains at least 100,000 objects larger than 100 kilometers, and the Oort cloud might contain 1 trillion or more comets. The combined mass is substantial, perhaps 10 to 100 times Earth's mass. This represents a significant fraction of the material that was originally in the outer solar system but didn't get incorporated into planets. It's a vast archive of primordial material, frozen and preserved for billions of years. A comet nucleus is often described as a dirty snowball, though that phrase doesn't capture the full complexity. Imagine a mixture of various ices, water ice dominant, but also frozen carbon dioxide, frozen methane, frozen ammonia, frozen carbon monoxide, mixed thoroughly with rocky dust, grains of silicate minerals, tiny particles of carbon, and complex organic molecules. Compress this mixture into an irregular body, anywhere from a few hundred meters to tens of kilometers across. The result is a comet nucleus, one of the most primitive objects in the solar system. Water ice dominates the composition, typically making up 60% to 80% of a comet's mass. This isn't pure water ice like you'd find in your freezer. It's contaminated with dust and other materials, making it darker and less reflective. Comet nuclei are among the darkest objects in the solar system, reflecting only 3% to 5% of the sunlight that hits them. They're darker than coal. The water ice exists in both crystalline and amorphous forms, depending on the temperature at which it condensed billions of years ago. Amorphous ice, formed at extremely low temperatures, is less ordered than crystalline ice and can trap other molecules within its structure. Carbon dioxide ice, also called dry ice, makes up perhaps 10% to 20% of a comet's volatile content. Carbon dioxide sublimates, turns from solid to gas, at much lower temperatures than water ice. Around 50 degrees Celsius below zero, carbon dioxide begins outgassing, while water ice remains solid. This means that as a comet approaches the Sun, carbon dioxide starts escaping before water does, driving activity at greater distances from our star. Other ices include methane, ammonia, carbon monoxide, and more complex molecules. Methane is familiar as natural gas on Earth. Ammonia is a compound of nitrogen and hydrogen, familiar from household cleaners. Carbon monoxide is a simple molecule that's toxic to humans, but common in space. These compounds exist as ices at the extremely low temperatures in the outer solar system. When heated, they sublimate and contribute to the comet's atmosphere and tail. The rocky component consists of silicate minerals, similar to those found in asteroids and on Earth. Olivine and pyroxene are common, magnesium and iron silicates that form in high-temperature environments. These grains probably condensed close to the Sun in the early solar system, then got transported outward and mixed with ices in the colder regions. The presence of high-temperature minerals in low-temperature comets tells us that material was thoroughly mixed in the protoplanetary disk. Dust didn't stay where it formed. Turbulence and gas flows transported it across vast distances. Carbon is present in multiple forms. Simple organic molecules, compounds of carbon, hydrogen, oxygen, and nitrogen are abundant. These include formaldehyde, methanol, ethane, and many others. More complex organics have also been detected, including long-chain hydrocarbons and possibly even amino acids, the building blocks of proteins. The exact inventory varies from comet to comet, but the presence of organic material is universal. Comets are rich in the chemical ingredients needed for life. Some comets show evidence of more complex carbon structures. Dark material coating the surface might include tholins, complex organic compounds formed by radiation processing of simpler molecules. When ultraviolet light or cosmic rays hit methane or other hydrocarbons, they break molecular bonds and allow atoms to recombine into larger, more complex structures. Over billions of years in the Oort cloud or Kuiper belt, this processing creates a layer of dark, carbon-rich material on the comet's surface. The internal structure of a comet nucleus isn't uniform. Some regions might be richer in ice, others richer in dust. Comets might have layered structures, like a partially mixed cake, with different compositions at different depths. They're probably highly porous, filled with voids and gaps, more like a loose rubble pile than a solid rock. This porosity affects how heat penetrates into the nucleus and how gases escape. The density of comet nuclei is surprisingly low, typically around 0.5 grams per cubic centimeter, half the density of water. This low density confirms the high porosity. A substantial fraction of a comet's volume is empty space, gaps between grains and chunks of material. This porous structure makes comets fragile. They can break apart under tidal stresses when passing close to massive planets or the Sun. Several comets have been observed to fragment, splitting into multiple pieces that then follow similar orbits. Isotopic ratios in cometary material provide clues about formation conditions. Hydrogen comes in two stable isotopes, regular hydrogen with 1 proton and deuterium with 1 proton and 1 neutron. The ratio of deuterium to hydrogen, DH ratio, varies depending on where and how water formed. Cometary water shows DH ratios different from Earth's oceans in some cases, similar in others. This has implications for whether comets delivered Earth's water. The evidence is mixed, suggesting that some comets might have contributed to Earth's oceans, while others have compositions that don't match. Other isotopic ratios, like oxygen-16 to oxygen-18 or carbon-12 to carbon-13, also provide information. These ratios depend on temperature, pressure, and chemical processes during formation. By measuring isotopes in cometary material and comparing them to samples from Earth, Mars, meteorites, and the Sun, we can trace the sources and mixing of material in the early solar system. Comets also contain trace amounts of more exotic materials. Presolar grains, tiny particles that formed around other stars before our solar system existed, have been found in meteorites and might exist in comets too. These grains have isotopic signatures that don't match anything formed in our solar system, marking them as interstellar visitors incorporated into the solar nebula. Finding such grains in comets would directly demonstrate that comets preserve material older than the solar system itself. The composition of comets varies somewhat from object to object, but the basic mix remains consistent. Water ice, carbon dioxide ice, other volatile ices, rocky dust, and organic molecules. This mixture reflects the chemistry of the outer protoplanetary disk 4.5 billion years ago. By studying comets, we're analyzing samples of the material from which the solar system formed, material that's been preserved in deep freeze, chemically unchanged for billions of years. Imagine existing in the Oort cloud, 50,000 astronomical units from the Sun, roughly a light year distant. At this distance, the Sun provides no perceptible heat. Its light is merely the brightest star in a sky filled with thousands of other stars. The temperature hovers around 5 degrees Kelvin, just 5 degrees above absolute zero. Nothing moves quickly here. Orbits take millions of years to complete. Time seems to have stopped, or at least slowed to a pace incomprehensible to human experience. A comet nucleus sits in this frozen realm, a dark, irregular body perhaps 10 kilometers across. Its surface temperature matches the surrounding space, heated only by the faint glow of starlight and the cosmic microwave background, the afterglow of the Big Bang. No atmosphere exists, no weather occurs. No erosion happens except for the occasional impact of a micrometeorite or the rare cosmic ray striking an atom and breaking a molecular bond. The comet has existed here since the solar system's formation, 4.5 billion years ago, essentially unchanged. This is the great strength of comets as scientific archives. Unlike Earth, where geological processes constantly reshape the surface, or even the Moon, which has been heated by impacts and radioactive decay, or asteroids that have been warmed and altered, comets in the outer reaches have experienced almost no processing. The ices and organic molecules they contain are as pristine as you can find in the solar system. They represent direct samples of the material from which everything formed. The isolation is profound. The nearest neighboring comet might be millions of kilometers away. The density of objects in the Oort cloud is incredibly low. If you stood on one comet and looked around, you wouldn't see any others with the naked eye. They'd be too far away and too dark. You'd see only stars, the same stars visible from Earth, arranged in the same constellations. The Oort cloud is mostly empty space with rare, isolated travelers drifting through it. Yet the comets aren't completely static. Slow processes occur even at these temperatures. Cosmic rays, high-energy particles from supernova remnants and other sources across the galaxy, strike the comet's surface. Each impact can break chemical bonds, creating free radicals that might recombine into new molecules. Over millions of years, this cosmic ray processing modifies the surface chemistry, creating complex organic compounds from simpler ones. The surface might darken as these compounds accumulate. Occasionally, very occasionally, something disturbs the comet's orbit. Perhaps a star passes within a light year of the Sun. Such close approaches happen every few million years. The star's gravity creates tidal forces that slightly alter the orbits of Oort cloud comets. Most changes are subtle, barely perceptible, but occasionally a comet's orbit changes enough that its perihelion, its closest approach to the Sun, drops below 5 astronomical units. The comet begins falling inward. The journey takes time. From the outer Oort cloud, it might take hundreds of thousands of years to fall to the inner solar system. During most of this time, nothing visible changes. The comet remains frozen, dark, inert. But as it crosses inside the orbit of Neptune, then Uranus, then Saturn, solar heating gradually increases. The surface temperature, which was 5 degrees Kelvin, rises to 10, then 20, then 50. Still incredibly cold by human standards, but warming. Around 5 astronomical units from the Sun, near Jupiter's orbit, surface temperatures reach approximately 130 degrees Kelvin, cold enough to freeze carbon dioxide on Earth, but warm enough for carbon dioxide ice to begin sublimating in the vacuum of space. The first gases start escaping from the comet nucleus. Carbon dioxide molecules, freed from the ice, stream away from the sunward side of the comet. The sublimation is still slow, releasing perhaps a few kilograms per second. Not enough to create a visible tail, but enough to mark the beginning of the comet's transformation. As the comet continues inward, the sublimation accelerates. At 3 astronomical units near the main asteroid belt, water ice reaches the sublimation temperature around 170 degrees Kelvin. Water vapor begins escaping, and the rate of gas production increases dramatically. Now hundreds of kilograms per second of gas are flowing away from the nucleus. Dust particles embedded in the ice are carried along by the gas flow, creating a cloud of gas and dust around the nucleus. This cloud, called the coma, grows larger as the comet approaches the Sun. By the time the comet reaches 2 astronomical units, roughly the orbit of Mars, the coma might extend 100,000 kilometers from the nucleus. It's larger than Jupiter. Yet the coma is incredibly tenuous. Its density is far lower than Earth's atmosphere, comparable to a laboratory vacuum. The total mass in the coma is only a few tons, spread across an enormous volume. The gases in the coma absorb ultraviolet light from the Sun, causing them to fluoresce and glow. The coma becomes visible through telescopes as a fuzzy patch of light surrounding the dark nucleus. The nucleus itself, even for the largest comets, remains too small to see as a disk from Earth. It appears only as a point of light embedded in the glowing coma. But the coma's glow makes the comet detectable, transforming it from an invisible dark speck into an observable object. For most of its existence, perhaps 99.99999% of the time since the solar system formed, the comet was frozen and invisible, waiting in the outer darkness. But now, falling toward the Sun after who knows what gravitational nudge sent it inward, the comet is waking up. The transformation has begun. The frozen time capsule is opening, releasing gases and dust that have been locked away for billions of years. Sublimation is the process by which a solid transforms directly into a gas without passing through a liquid phase. On Earth, we see sublimation when dry ice, solid carbon dioxide, turns into carbon dioxide gas without melting into liquid. Or when snow disappears on a cold, sunny day without becoming liquid water first. In the vacuum of space, where atmospheric pressure is negligible, sublimation is the only way ices can vaporize. There's no pressure to maintain a liquid phase, so solids go directly to gas. The rate of sublimation depends on temperature and the specific material. Each substance has its own sublimation curve, a relationship between temperature and vapor pressure. For water ice, sublimation becomes significant at temperatures above roughly 170 degrees Kelvin in vacuum. Below that temperature, water molecules occasionally escape from the ice surface, but the rate is extremely low. Above 170 Kelvin, the rate increases exponentially with temperature. At 200 Kelvin, water sublimates perhaps 1,000 times faster than at 170 Kelvin. The energy for sublimation comes from sunlight. As a comet approaches the Sun, solar radiation strikes its surface. Dark material absorbs this radiation, converting it to heat. The heat conducts into the ice beneath, raising its temperature. When the ice reaches the sublimation temperature, molecules begin escaping as gas. This gas carries away heat, the latent heat of sublimation, which cools the surface. A balance is reached where incoming solar energy equals the energy carried away by sublimating gas plus the energy re-radiated as infrared radiation. The geometry matters. The side of the comet facing the sun receives direct sunlight and heats most intensely. Sublimation occurs primarily from the sunward side. The night side, facing away from the sun, remains colder and sublimates much more slowly. This creates an asymmetry. Gas streams predominantly from the day side, and the comet develops a lopsided atmosphere, denser on one side than the other. Rotation complicates the picture. Comets rotate, typically with periods of hours to days. As the comet spins, different areas move in and out of sunlight. When a region enters sunlight after being in shadow, it heats up and sublimation increases. When it rotates into shadow, it cools and sublimation decreases. This creates periodic variations in gas production. Some comets show distinct jets or plumes of gas and dust that activate when specific surface features rotate into sunlight. The surface of a comet nucleus isn't uniform. Some areas might be covered with darker dust that's been left behind as ice sublimated. These regions absorb more sunlight and heat more effectively, but they can also insulate underlying ice, slowing sublimation. Other areas might have fresh ice exposed, which sublimates readily. Active regions, where gas and dust are actively escaping, might cover only a small percentage of the total surface. Most of the nucleus could be inactive, covered with a dust mantle that prevents or reduces gas release. The thickness of this dust mantle affects how quickly a comet's activity evolves. If the mantle is thin, gas can escape easily, carrying dust away and exposing fresh ice. But if the mantle is thick, it insulates the ice beneath. Heat penetrates slowly through the dust. Sublimation occurs at depth, and gas pressure builds beneath the surface until it's strong enough to break through, creating localized outbursts or jets. The thermal inertia of the comet material also matters. Thermal inertia is a measure of how quickly a material responds to temperature changes. High thermal inertia means the material heats and cools slowly, storing heat effectively. Low thermal inertia means rapid heating and cooling. For comets, thermal inertia is generally low because of their high porosity. Heat doesn't conduct well through the porous ice-dust mixture. This means the surface temperature responds quickly to sunlight, heating rapidly when illuminated, and cooling rapidly when in shadow. The depth to which solar heating penetrates depends on thermal conductivity and the rotation period. For a comet rotating once per day, solar heating affects the top meter or so of the surface. Beneath that depth, temperatures remain constant, determined by the overall energy balance of the nucleus. For slowly rotating comets or regions near the poles, heating might penetrate deeper, potentially reaching several meters. As gas sublimates from the ice, it expands into the vacuum surrounding the comet. The gas molecules, initially at the temperature of the ice surface, accelerate as they expand, reaching speeds of around 0.5 kilometers per second for water vapor. This expansion is adiabatic, meaning the gas cools as it expands. By the time water vapor has moved a few kilometers from the nucleus, it might have cooled to 50 or 100 degrees Kelvin, much colder than the nucleus surface. Dust particles embedded in the ice are dragged along by the expanding gas. Whether a particle gets lifted depends on its size and the gas flow rate. Small particles, microns to millimeters in size, are easily carried. Larger particles, centimeters or more, might be too heavy for the gas to lift, and they remain on the surface, contributing to the dust mantle. The size distribution of lifted particles affects the comet's appearance and the brightness of its dust tail. The total mass loss rate from a comet depends on its size, the intensity of solar radiation, the composition, and the fraction of the surface that's active. For a comet near 1 astronomical unit from the Sun, a typical water production rate might be several tons per second. Dust production is harder to estimate, but might be comparable. Over the course of a comet's passage through the inner solar system, perhaps a few weeks to months near perihelion, the comet might lose millions of tons of material. For a comet nucleus with a mass of tens of billions of tons, this represents a small fraction, perhaps 0.1% to 1% of the total mass. But repeated passages add up. A short period comet that returns every few years or decades loses material each time. After hundreds or thousands of orbits, the comet's ices become depleted. What remains is a dark, inert body, essentially an asteroid composed of the rocky dust that was mixed with the ice. Some asteroids we observe today might be extinct comets, objects that originated in the Kuiper Belt, but have lost all their volatiles. Distinguishing extinct comets from true asteroids is challenging, but orbital characteristics can provide clues. Objects with comet-like orbits, but no observed activity might be dormant or extinct comets. The coma is the vast atmosphere surrounding the nucleus, a region where gases released from the ice expand and react with sunlight. Understanding the coma requires understanding the chemistry and physics of these gases as they move away from the nucleus and interact with solar radiation. The coma is where much of what we observe as a comet happens. It's the interface between the frozen nucleus and the larger structures, the hydrogen cloud and the tails, that extend for millions of kilometers. Water vapor dominates the gases released from most comets. As water molecules, H2O, stream away from the nucleus, they move through a region where ultraviolet light from the sun is intense. Ultraviolet photons carry enough energy to break molecular bonds. When a UV photon strikes a water molecule, it can dissociate it, breaking it into smaller fragments. The most common result is OH, hydroxyl radical, plus H, a hydrogen atom. Both fragments continue moving outward. The hydroxyl radical, OH, is itself unstable. It can absorb another UV photon and dissociate into O, oxygen atom, plus H. So a single water molecule, after exposure to UV light, eventually becomes one oxygen atom and two hydrogen atoms, all moving independently. These atoms don't recombine into molecules because the density is too low for collisions that would allow recombination. Instead, they spread outward, creating a vast cloud of atomic hydrogen and oxygen around the comet. The hydrogen atoms, being the lightest, move fastest and travel farthest. They form a huge hydrogen cloud, sometimes called the hydrogen envelope, that can extend millions of kilometers from the nucleus. This cloud is invisible to the human eye, but it glows in ultraviolet light due to a process called resonance scattering. Hydrogen atoms absorb UV light from the sun at a specific wavelength, 121.6 nanometers, called Lyman alpha. They then re-emit this light in random directions. Spacecraft with UV detectors can observe this Lyman alpha glow, revealing the extent of the hydrogen cloud. The hydrogen cloud is enormous. For a large active comet, the hydrogen envelope might reach 10 million kilometers in radius, larger than the Sun. Yet the total mass in this cloud is tiny, perhaps a few tons. The density is incredibly low, only a few hundred atoms per cubic centimeter in the inner coma, dropping to a few atoms per cubic centimeter in the outer envelope. For comparison, Earth's atmosphere at sea level has about 10 to the 19th power molecules per cubic centimeter. The coma is a better vacuum than anything we can create in laboratories on Earth. Other molecules released from the nucleus also undergo photodissociation. Carbon dioxide, CO2, breaks into CO, carbon monoxide, and O, atomic oxygen. Carbon monoxide is relatively stable and doesn't dissociate easily, so it remains molecular and contributes to the coma's molecular content. Methane, CH4, breaks into various fragments including CH3, CH2, CH, and individual carbon and hydrogen atoms. Ammonia, NH3, breaks into NH2, NH, N, and H. All these processes create a complex mixture of atoms, molecules, ions, and radicals. Some of these species fluoresce when they absorb sunlight. Fluorescence is the process where a molecule absorbs a photon at one wavelength and re-emits a photon at a different, typically longer wavelength. The energy difference between the absorbed and emitted photons goes into exciting vibrational or rotational states of the molecule. Several molecular species in cometary comas fluoresce strongly, making them visible through telescopes. Cn, the cyanogen radical, fluoresces in the violet and blue part of the spectrum. C2, a two-carbon molecule called dicarbon, also fluoresces in the blue-green. C3, a three-carbon linear molecule, fluoresces in the blue and violet. These molecules give comets some of their color, a greenish or bluish tint that's visible in photographs. The human eye, adapted to see yellowish-green light most efficiently, often perceives bright comets as greenish due to emissions from C2 and Cn. Sodium atoms, present in small amounts, emit a strong yellow-orange light when excited by sunlight. This sodium emission, similar to the glow of sodium vapor street lamps, can sometimes be detected in the coma. The origin of sodium in comets isn't entirely clear, but it's probably related to the silicate dust mixed with the ice. The chemistry in the coma is further complicated by ionization. Ultraviolet light and the solar wind can strip electrons from atoms and molecules, creating ions. Water molecules can be ionized to H2O+, water ion. Carbon dioxide becomes CO2+. These ions are electrically charged and respond to magnetic fields. The solar wind, a stream of charged particles flowing from the sun, carries a magnetic field with it. This field sweeps through the coma, interacting with the ions and affecting their motion. The interaction between the solar wind and the coma creates complex electromagnetic effects. The solar wind tries to push ions away from the sun, while the comet's weak gravity and the pressure of sublimating gas try to hold them. The result is a dynamic boundary region where the solar wind flow is deflected around the comet, similar to how water flows around a rock in a stream. This creates a bow shock, a region where the solar wind slows and heats as it encounters the obstacle presented by the coma. Inside the coma, collisions between particles are rare, but not impossible. In the inner coma, close to the nucleus where the density is highest, molecules might collide occasionally. These collisions can transfer energy, affect temperatures, and even drive chemical reactions. But as the gas expands and density drops, collisions become increasingly unlikely. In the outer coma, particles are essentially in free flight, moving ballistically without interacting with other particles. Temperature structure of the coma is complex. Near the nucleus, temperatures might be several hundred degrees Kelvin due to solar heating and collisional warming. Farther out, where collisions cease, the temperature of the gas is determined by the balance between radiative heating from the sun and radiative cooling by the gas emitting infrared photons. For water and other molecules, this can result in temperatures of 100 to 200 degrees Kelvin in the outer coma. But because the density is so low, the concept of temperature becomes less meaningful. In a near vacuum, temperature describes the average kinetic energy of particles, but it doesn't translate into sensations of hot or cold the way it does in Earth's atmosphere. The coma evolves as the comet moves through its orbit. Approaching the sun, activity increases, the coma grows larger and denser, and the production rates of gas and dust rise. At perihelion, closest approach to the sun, the comet reaches peak activity. Then, as it recedes, activity decreases, the coma shrinks, and the comet fades. Monitoring this evolution provides information about how the nucleus responds to solar heating and how its activity changes with distance. While gases dominate the mass in the coma, dust dominates what we see. The dust particles, ranging from submicron size to millimeters or more, scatter sunlight, making the coma and tail visible. Understanding the dust component is crucial for interpreting observations and for understanding the nature of cometary nuclei. Dust in comets is a mixture of materials. Silicate minerals, similar to those found in asteroids and on Earth, are abundant. These include olivine, pyroxene, and other magnesium, iron, and silicon compounds. The dust also contains carbon-rich materials, organic compounds ranging from simple molecules to complex tars. Some dust might be pure carbon in the form of graphite or amorphous carbon. Iron and nickel grains, similar to those found in meteorites, are also present. The size distribution of dust particles follows a pattern. There are many small particles and fewer large ones, with the number decreasing as size increases. This distribution is often described by a power law, where the number of particles drops off with some power of the size. The exact slope of this power law varies from comet to comet, and even within a single comet's evolution. Small particles, microns in size, are easily lifted by gas flow and dominate the visible scattering of light. These particles are comparable in size to the wavelength of visible light, making them effective scatterers. Larger particles, while fewer in number, contribute significantly to the total mass. A single millimeter-sized particle has the mass of 1 billion micron-sized particles. So even though large particles are rare, they represent a substantial fraction of the total dust mass. The composition of individual dust particles can be complex. Some particles are aggregates, loosely bound collections of smaller grains stuck together. These aggregates can be fluffy and porous, with densities much lower than the materials they're made from. Imagine a cluster of tiny grains, each micron-sized, held together by weak forces. The cluster might be 100 microns across, but mostly empty space. Such particles are fragile and can break apart easily. When dust is released from the nucleus, it's accelerated by the expanding gas. The acceleration depends on the particle size and the gas flow rate. Small particles are accelerated efficiently, reaching speeds comparable to the gas velocity, around 0.5 kilometers per second. Larger particles are harder to accelerate and might reach only a fraction of this speed. The differential acceleration means that small particles move outward faster than large ones, creating a size-dependent distribution in the coma. As dust moves away from the nucleus, it continues to scatter sunlight, contributing to the coma's brightness. The scattering efficiency depends on particle size and composition. For particles smaller than the wavelength of light, scattering is weak. For particles comparable to the wavelength, scattering is maximized. For particles much larger than the wavelength, scattering becomes less efficient per unit mass. The color of scattered light provides information about particle size. Small particles scatter blue light more efficiently than red light, similar to why Earth's sky is blue. Large particles scatter all colors more equally, producing white light. By measuring the color of light scattered by dust in the coma, astronomers can infer the typical particle size. Observations show that cometary dust is generally reddish, indicating that larger particles, several microns or more, are common. Dust in the coma also absorbs and emits thermal infrared radiation. Sunlight heats the dust particles, and they re-radiate this energy as infrared photons. The temperature of dust particles depends on their size, composition, and distance from the sun. Near the nucleus, dust might be heated to several hundred degrees Kelvin. Farther out, temperatures drop. By observing the infrared emission from dust, we can estimate its temperature and, combined with models, infer properties like particle size and composition. The dust production rate is one of the key parameters characterizing a comet. It's typically expressed in kilograms per second. For an active comet near 1 astronomical unit from the Sun, dust production might range from a few kilograms per second to hundreds of kilograms per second, depending on the comet's size and activity level. The dust-to-gas mass ratio, comparing dust production to gas production, is another important parameter. This ratio varies from comet to comet and might range from 0.1 to 10, meaning comets can produce anywhere from 10 times more gas than dust to 10 times more dust than gas. The dust released from a comet doesn't stay in the coma. It moves outward, pushed by gas pressure near the nucleus and then affected by radiation pressure from sunlight. Radiation pressure is the momentum carried by photons. When sunlight reflects off a dust particle, it imparts a small push. For small particles, this push can be significant compared to the sun's gravitational pull. The ratio of radiation pressure, force to gravitational force, is called beta. For particles around 1 micron in size, beta is approximately 1, meaning radiation pressure equals gravity. For smaller particles, radiation pressure exceeds gravity, and they're pushed away from the sun. For larger particles, gravity dominates, and they fall back toward the sun. This differential effect creates the dust tail. Particles of different sizes are pushed to different degrees, spreading out along a curved path that points generally away from the sun, but curves slightly in the direction of the comet's motion. The dust tail is the white or yellowish tail visible in photographs of bright comets. It's composed of sunlight scattered by millions or billions of dust particles, each following its own trajectory determined by its size and the forces acting on it. Dust released from a comet can also contribute to zodiacal light, a faint glow visible in the night sky along the ecliptic, the plane of the solar system. Zodiacal light is sunlight scattered by interplanetary dust, much of which comes from comets. Each time a comet passes through the inner solar system, it deposits dust along its orbit. Over time, this dust spreads out, forming a diffuse cloud throughout the solar system. From Earth, we see zodiacal light as a faint triangular glow extending from the horizon after sunset or before sunrise. Meteor showers are another consequence of cometary dust. When Earth's orbit crosses the orbit of a comet, we pass through the stream of dust left behind. Dust particles, traveling at tens of kilometers per second relative to Earth, enter the atmosphere and burn up due to friction, creating meteors or shooting stars. The timing and direction of meteor showers are predictable because they're associated with specific comets. The Perseids in August come from Comet Swift-Tuttle. The Leonids in November come from Comet Tempel-Tuttle. The Orionids in October come from Halley's Comet. Observing meteor showers provides indirect information about the dust production of comets over long timescales. When you see a bright comet in the sky, you're typically seeing two distinct tails, though they can blend together, or one might dominate depending on the comet's activity and viewing geometry. These two tails are fundamentally different in composition, appearance, and the forces that shape them. Understanding both is essential to grasping how comets interact with the sun and the solar wind. The dust tail is the one most people picture when they think of comets. It's composed of dust particles that scatter sunlight, appearing white or yellowish, sometimes with a slightly reddish tint. The dust tail is broad and curved, often extending millions of kilometers in a graceful arc that points generally away from the sun but curves somewhat in the direction of the comet's orbital motion. This curvature happens because dust particles, once released from the nucleus, continue in their own orbits around the sun. But those orbits are modified by radiation pressure. Smaller particles are pushed more strongly than larger ones, creating a spread of trajectories. The result is a fan-shaped structure that creates the characteristic sweeping appearance. Dust tail lengths vary enormously. Some comets develop tails only a few 100,000 kilometers long, barely visible from Earth. Others produce spectacular tails stretching 100 million kilometers or more, enough to span a significant fraction of Earth's orbit. The Great Comet of 1843 had a dust tail estimated at 300 million kilometers long, twice the distance from Earth to the Sun. Such a tail, if placed with its beginning at the Sun, would extend past Mars toward the asteroid belt. The brightness of the dust tail depends on how much dust the comet is producing, the size distribution of particles, and the viewing geometry. When we see a comet nearly edge-on, looking along its orbital plane, the dust tail can appear very long because we're seeing the entire extent compressed into our line of sight. When viewed more face-on, looking down on the orbital plane, the tail appears shorter. This geometric effect can make the same comet look very different from one observation to the next as Earth's position relative to the comet's orbit changes. The ion tail, also called the plasma tail or gas tail, is distinctly different. It's composed of ionized gas molecules, primarily water ions, H2O+, but also carbon monoxide ions, CO+, carbon dioxide ions, CO2+, and others. These ions emit light through fluorescence, glowing in specific colors. The most prominent emission comes from CO+, which fluoresces in blue and blue-green wavelengths, giving the ion tail a characteristic bluish color that contrasts with the yellowish dust tail. The ion tail is shaped by entirely different forces than the dust tail. While radiation pressure affects dust, the ion tail is controlled by the solar wind and its embedded magnetic field. The solar wind flows away from the Sun at speeds of 400 to 800 kilometers per second, carrying magnetic field lines with it. These field lines sweep past the comet. Ions in the coma get caught by the magnetic field and are dragged along with it, streaming directly away from the Sun. Because the solar wind moves much faster than dust particles, and because ions are tied to the magnetic field lines, the ion tail points almost directly away from the Sun with very little curvature. It's straight and narrow compared to the dust tail, sometimes described as looking like a searchlight beam or an arrow shot from the comet's head. The ion tail can be extremely long, extending 100 million kilometers or more, but because it's thin and the Shakyan, emission is relatively faint. It's often less visually impressive than a bright dust tail. The ion tail's appearance can change rapidly. Fluctuations in the solar wind cause variations in the tail's brightness and structure. Sometimes the tail develops kinks or disconnection events where a section of the tail breaks off and drifts away while a new tail forms. These disconnection events occur when the magnetic field configuration in the solar wind changes suddenly, severing the connection between the coma and the tail. The disconnected section, no longer attached to the nucleus, continues moving outward and eventually disperses. Meanwhile, a new ion tail grows from the coma. The two tails together create the classic appearance of a bright comet. The broad, sweeping dust tail provides much of the visual brightness and the graceful curved shape. The narrow, straight ion tail adds a bluish component and points like an indicator showing the direction away from the Sun. From Earth, when a comet is well placed for viewing, both tails can be seen distinctly, and photographs reveal the color difference between the yellowish dust and the blue ion plasma. The relative prominence of the two tails varies from comet to comet and throughout a single comet's passage through the inner solar system. Some comets are dust-rich, producing impressive dust tails, but weak ion tails. Others are gas-rich, creating prominent ion tails while their dust tails remain faint. The dust-to-gas ratio affects this balance. Comets with low dust-to-gas ratios produce more prominent ion tails. Comets with high dust-to-gas ratios show more impressive dust tails. The orientation of Earth relative to the comet's orbit also affects what we see. When the comet is positioned such that we're looking along its orbit, Both tails can appear to point away from us, creating a fan-like or sunburst appearance. When the comet is to one side of the sun from Earth's perspective, we see the tails in profile, and the two tails' different curvatures and directions become most apparent. The antitail is an occasional phenomenon where a comet appears to have a tail pointing toward the sun. This isn't a real tail, but a viewing geometry effect. It occurs when Earth passes through the plane of the comet's orbit, and we look edge-on at the dust trail. The dust particles, spread along the comet's orbit, appear from our perspective to create a structure pointing in various directions, including toward the sun. It's an illusion created by perspective, but it can be dramatic and was historically confusing before astronomers understood the geometry involved. Observing both tails provides different information about the comet. The dust tail tells us about dust production, particle size distribution, and how dust is released from the nucleus. The ion tail tells us about gas production, the composition of gases, and how the solar wind interacts with the coma. Together, they give a comprehensive picture of cometary activity. The solar wind is one of the sun's most significant influences on comets, yet it's invisible and was unknown until the mid-20th century. Understanding the solar wind and how it interacts with cometary comae and ion tails requires understanding both the nature of the solar wind itself and the physics of plasmas and magnetic fields in space. The sun continuously loses mass. Approximately 1 million tons per second of material streams away from the sun's outer atmosphere, the corona, into space. This stream, the solar wind, consists primarily of electrons and protons, with smaller amounts of helium nuclei and trace amounts of heavier ions. These particles move fast, typically 400 kilometers per second near Earth's orbit, though speeds can range from 300 to 800 kilometers per second, depending on solar activity. The solar wind originates in the corona, where temperatures exceed 1 million degrees Kelvin. At such high temperatures, atoms are fully ionized. Electrons have been stripped away, leaving bare nuclei. The thermal energy is so great that the particles move faster than the sun's escape velocity. They stream outward, carrying energy and momentum away from the sun. As the solar wind expands, it cools, but it remains ionized even at Earth's orbit and far beyond. Embedded in the solar wind is the sun's magnetic field. The sun's rotation and the outward flow of the solar wind combine to give the magnetic field a spiral structure called the Parker spiral after physicist Eugene Parker, who predicted the solar wind's existence. Magnetic field lines extend outward from the sun, but also sweep around due to rotation, creating spiral arms that fill the solar system. This magnetic field is carried by the solar wind plasma and can't be separated from it. When the solar wind encounters a comet, several things happen. The expanding coma creates an obstacle to the flow. The solar wind can't penetrate the dense inner coma because the magnetic field is frozen into the plasma, a principle from magnetohydrodynamics that states plasmas and magnetic fields move together. As the solar wind approaches the comet, it's deflected, flowing around the obstacle much like water flows around a rock. This deflection creates a bow shock, a boundary where the solar wind slows from supersonic to subsonic speeds. Supersonic here means faster than the speed of waves in the plasma, similar to how an airplane creates a shock wave when it exceeds the speed of sound in air. The bow shock forms at some distance from the nucleus, depending on the comet's activity and the solar wind conditions. For an active comet, the bow shock might be located hundreds of thousands of kilometers upstream in the direction the solar wind is coming from. Inside the bow shock, the solar wind is slowed and heated, but it continues to flow around the comet. Eventually, it reaches a boundary where the outward flow of gas from the coma balances the inward pressure of the solar wind. This boundary, called the contact surface or cum topors, separates the coma, dominated by cometary gas, from the region dominated by solar wind plasma. The contact surface isn't a sharp boundary, but a transition region where both plasmas mix. The ion tail forms from this interaction region. Cometary ions, created by photoionization and electron impact ionization in the coma, are picked up by the solar wind magnetic field. Once ionized, a molecule responds to electromagnetic forces. The magnetic field exerts a force on moving charged particles, causing them to spiral around field lines. This process, called pickup, accelerates the ions and carries them away from the comet, streaming in the anti-sunward direction along the magnetic field lines. The pickup process extracts energy from the solar wind, slowing it further. The solar wind has to do work to accelerate the newly created ions. This energy transfer contributes to heating the region around the comet. The process also loads mass into the solar wind flow, increasing its density and changing its properties downstream from the comet. The ion tail structure reflects the magnetic field configuration. Since ions are tied to field lines, they trace out the magnetic geometry. Fluctuations in the solar wind cause corresponding fluctuations in the tail. When the solar wind speed increases, the tail brightens and extends. When the speed decreases, the tail dims and contracts. Changes in the magnetic field direction can cause the tail to wave or develop kinks. Disconnection events, mentioned earlier, are dramatic illustrations of this interaction. They occur when the solar wind carries a boundary between regions of opposite magnetic polarity past the comet. Such boundaries, called sector boundaries or magnetic sector boundaries, divide the solar wind into regions where the magnetic field points in different directions. When a sector boundary crosses the comet, it can sever the connection between the tail and the coma. The magnetic topology changes, and the old tail, no longer connected, drifts away. A new tail forms as fresh ions from the coma are picked up by the solar wind with its new magnetic field direction. These events can happen over hours or days, fast enough that they're observable. Astronomers have captured images showing a comet with a fragmented tail, pieces of the old tail drifting away while a new one grows. Disconnection events provide direct visual evidence of the solar wind's structure and its interaction with comets. The solar wind's intensity varies with solar activity. During periods of high solar activity, when the sun is covered with sunspots and is more active, the solar wind is stronger and more variable. During solar minimum, the quietest part of the 11-year solar cycle, the solar wind is steadier and less intense. Comets observed during different phases of the solar cycle can show different behaviors, with more active solar wind conditions leading to more dramatic ion tail structures and more frequent disconnection events. Spacecraft observations have revolutionized our understanding of these interactions. Missions like Giotto, which flew through Halley's Comet in 1986, directly measured the plasma environment and magnetic field structure around a comet. More recently, the Rosetta mission orbited Comet 67P for 2 years, continuously monitoring the solar wind interaction as the comet approached and receded from the Sun. These observations revealed the complexity and dynamism of the comet-solar wind interaction in unprecedented detail. Throughout human history, bright comets have appeared in the sky, provoking awe, fear, and curiosity. Before the scientific era, comets were interpreted as omens, messages from the gods, or signs of impending disaster. After the development of astronomy as a science, comets became objects of study, their appearances recorded and their motions analyzed. Some comets have appeared repeatedly, becoming familiar visitors. Others appear once and vanish forever. Here on Whispering Universes, let's trace the stories of some of the most famous comets, objects that have shaped our understanding of these frozen wanderers. Halley's Comet is perhaps the most famous. It's named after Edmund Halley, the English astronomer who in 1705 realized that comets observed in 1531, 1607, and 1682 were likely the same object returning on a roughly 76-year orbit. Halley used Newton's newly developed theory of gravity to calculate the comet's orbit and predicted it would return in 1758. He didn't live to see the return. He died in 1742. But when the comet appeared on schedule in late 1758, his prediction was vindicated, and the comet was named in his honor. Halley's comet has been observed for over 2,000 years. Records of its appearances go back to at least 240 BCE, documented in Chinese astronomical records. The comet appears roughly every 76 years, though the exact period varies slightly due to gravitational perturbations from Jupiter and other planets. The most recent appearance was in 1986, when a fleet of spacecraft, including ESA's Giotto and 2 Soviet Vega probes, visited the comet, taking the first close-up images of a cometary nucleus and measuring its properties directly. The 1986 apparition was disappointing for casual observers from Earth. The viewing geometry was poor, with the comet never getting very close to Earth and appearing relatively faint. But for scientists, it was transformative. Images showed the nucleus as a dark, potato-shaped object roughly 15 kilometers long and 8 kilometers wide. The surface was darker than coal, reflecting only 4% of the sunlight hitting it. Jets of gas and dust streamed from active regions covering perhaps 10% of the surface. These observations confirmed many theoretical predictions, but also revealed surprises, including the extreme darkness of the surface and the localized nature of activity. Halley's comet will return in 2061. Based on orbital calculations, it should be well placed for viewing from Earth, potentially becoming a prominent naked eye object. For those of us who weren't alive or old enough to remember the 1986 apparition, the 2061 return offers a future opportunity to witness this historic comet. Comet Hale-Bopp, discovered in 1995, became one of the brightest comets of the 20th century. It was unusually large, with a nucleus estimated at 40 to 80 kilometers in diameter, several times larger than Halley's. When it reached perihelion in 1997, at a distance of 0.914 astronomical units from the Sun, it was visible to the naked eye for 18 months, an extraordinarily long period. Hale-Bopp developed both a bright dust tail and a prominent blue ion tail, making it visually spectacular. Hale-Bopp's orbit suggested it was a long-period comet, making one of its first visits to the inner solar system from the Oort cloud. Its large size meant that it still contained most of its original ices, making it exceptionally active. Gas production rates were enormous, up to several hundred tons per second. The comet provided a rare opportunity to study a pristine comet, one that hadn't been repeatedly heated by previous passages near the Sun. The Great Comet of 1811 was visible for 260 days, longer than any comet in recorded history. At its brightest, it rivaled Halley's comet and was easily visible even from cities. The comet appeared during a time of social upheaval, the Napoleonic Wars, and its appearance became woven into the events of that era. Tolstoy mentioned it in War and Peace, giving it a place in literature as well as astronomy. Comet shoemaker Levy 9 became famous not for its appearance from Earth, but for its spectacular end. Discovered in 1993, the comet had been captured into orbit around Jupiter and had been torn apart by tidal forces, breaking into more than 20 fragments. These fragments, strung out like pearls on a necklace, were on a collision course with Jupiter. In July 1994, the world watched as the fragments plunged into Jupiter's atmosphere one by one over the course of a week. Each impact released energy equivalent to millions of nuclear bombs, creating dark scars in Jupiter's clouds that persisted for months. The impacts were observable from Earth with backyard telescopes and professional observatories, along with the Hubble Space Telescope and space probes in the Jupiter system, captured detailed data. The event provided unprecedented information about cometary composition, impact physics, and Jupiter's atmosphere. It also dramatically illustrated that impacts are still occurring in the solar system, and that Jupiter, with its immense gravity, shields the inner solar system from some potential impactors. Comet Hyakutake in 1996 passed very close to Earth, only 15 million kilometers, one of the closest approaches on record. Despite not being an exceptionally large or active comet, its proximity made it appear spectacular. The ion tail extended more than 100 degrees across the sky, spanning from horizon to horizon. The tail's structure was visible to the naked eye, with streamers and waves caused by solar wind variations. Hyakutake provided excellent opportunities for amateur and professional observations, and its close approach allowed detailed spectroscopic studies of its composition. Comet Ison, discovered in 2012, generated enormous excitement because predictions suggested it could become exceptionally bright, possibly the comet of the century. It was projected to pass very close to the Sun, only 1.2 million kilometers from the solar surface at perihelion in November 2013. The intense solar heating was expected to cause spectacular activity. Unfortunately, Ison didn't survive perihelion. As it approached the Sun, the nucleus likely fragmented and evaporated. What remained after perihelion was only a diffuse cloud of dust, quickly fading. Ison's demise, while disappointing, provided valuable data on how comets can disintegrate when subjected to extreme solar heating. These famous comets, and many others, have advanced our understanding immensely. Each provides unique data, revealing aspects of cometary behavior and composition. They remind us that comets are individuals, varying in size, composition, activity, and orbital history. They also connect us to the long history of human observation, linking our modern scientific understanding to the awe and wonder felt by observers throughout millennia. Observing comets from Earth provides limited information. Telescopes reveal the coma and tails, spectroscopy measures composition, but the nucleus remains too small and faint to study in detail. To truly understand comets, spacecraft must visit them. Since the 1980s, multiple missions have flown past comets, orbited them, and even landed on their surfaces, transforming our knowledge. The first close encounters occurred in 1986 when a fleet of spacecraft flew past Halley's Comet. The European Space Agency's Giotto probe approached within 600 kilometers of the nucleus, closer than any previous spacecraft had come to a comet. Giotto carried cameras and instruments to measure gas and dust. As it plunged through the coma, dust impacts damaged some instruments and knocked the spacecraft off its pointing, but it survived and returned valuable data. Giotto's images revealed the nucleus as an irregular, elongated body, dark and rough. Jets of gas and dust emerged from specific regions, while most of the surface appeared inactive. The nucleus was rotating, and as different areas turned into sunlight, jet activity waxed and waned. The mission confirmed that cometary nuclei are covered with a dark crust of organic material and dust, insulating the ice beneath. Two Soviet Vega spacecraft also flew past Halley, though at greater distances, roughly 8,000 kilometers. Japanese spacecraft, Sakigake and Suisei, observed from even farther away, focusing on the ion tail and solar wind interaction. Together, these missions provided a comprehensive data set, the Halley Armada offering humanity's first detailed look at a comet. In 2001, NASA's Deep Space One mission, primarily a technology demonstration, flew past Comet Borrelly. The images showed a nucleus about 8 kilometers long, with smooth regions and rougher terrain. Jets emerged from discrete sources, and the surface appeared layered, suggesting a complex structure built up over time. Stardust, launched in 1999, flew through the coma of Comet Wild 2 in 2004. Its primary goal was to collect samples of cometary dust and return them to Earth. Using aerogel, an ultralight material that could capture dust particles without destroying them, Stardust collected thousands of grains as it flew through the coma at a relative speed of 6 kilometers per second. The sample return capsule landed in Utah in 2006. Analysis of the returned samples revealed surprising complexity. The dust contained high-temperature minerals, materials that formed close to the Sun in the early solar system. This confirmed that material was transported from the inner solar system to the outer regions, mixing thoroughly in the protoplanetary disk. The samples also contained organic compounds, including amino acids supporting the idea that comets could have delivered prebiotic molecules to early Earth. Deep Impact, launched in 2005, performed a dramatic experiment. The spacecraft released an impactor, a 370-kilogram copper projectile, which struck Comet Tempel 1 at 10 kilometers per second. The impact excavated material from beneath the surface, creating a bright flash and a plume of gas and dust that was observed by the spacecraft and telescopes on Earth. The goal was to reveal pristine material from the comet's interior, unaltered by solar heating. The impact released more dust than expected, obscuring some observations, but it provided valuable data. The material ejected was finer than anticipated, suggesting the nucleus was more porous and fragile than models predicted. Spectroscopy of the plume revealed water ice and various organic compounds, confirming the composition of the interior was similar to predictions, but with variations in dust properties. Rosetta, perhaps the most ambitious comet mission, was launched in 2004 and reached Comet 67P Churyumov-Gerasimenko in 2014. Rather than flying past, Rosetta entered orbit around the comet and remained there for 2 years, following it through perihelion. This allowed continuous monitoring of the comet's evolution as it approached and then receded from the Sun. Rosetta's cameras mapped the nucleus in stunning detail, revealing a bizarre shape resembling a rubber duck, with 2 lobes connected by a narrow neck. The surface displayed diverse terrains, smooth regions covered with dust, rough areas with exposed boulders and cliffs, pits that might be collapse features or sublimation vents. Jets emerged from specific locations, and their activity changed as the comet rotated and as it moved through its orbit. Rosetta measured gas and dust, production rates, composition, nucleus temperature, and many other parameters. It observed the nucleus up close for months, capturing changes as solar heating increased activity. The mission also deployed a lander, Philae, which touched down on the comet's surface in November 2014. The landing didn't go as planned. Philae bounced and ended up in a shadowed location, limiting its operations, but it returned data from the surface, including measurements of the nucleus's mechanical strength and composition. Rosetta's observations revealed that 67P has 2 distinct lobes, suggesting it might be a contact binary, 2 separate bodies that gently collided and stuck together. The comet's rotation was complex, with the nucleus tumbling in space. Water production peaked not at perihelion, but a few weeks after, suggesting complex thermal processes in the nucleus. The DH ratio in the comet's water was significantly higher than Earth's oceans, suggesting that comets like 67P were not the primary source of Earth's water. These missions collectively have transformed our understanding. Cometary nuclei are dark, irregular, and fragile. Their surfaces are complex, with active regions covering only a small fraction. The composition includes high-temperature minerals mixed with ices and organics, evidence of thorough mixing in the early solar system. Comets are diverse, each nucleus having its own characteristics, but the basic structure and processes are consistent. Future missions are planned or proposed. Concepts include sample return missions to bring back larger amounts of material, penetrators to probe beneath the surface, and long-duration orbiters to study multiple comets. Each mission builds on previous ones, refining our understanding and raising new questions. Earth is a water world. Oceans cover 70% of the surface, holding roughly 1.4 billion cubic kilometers of water. Where did all this water come from? This question has profound implications for understanding Earth's formation and for assessing the likelihood of water, and thus potentially life, on other planets. Comets have long been considered potential contributors, frozen reservoirs that delivered water during the final stages of Earth's formation. In the standard model of solar system formation, Earth formed from material in the inner solar system, where temperatures were too high for water ice to condense. The building blocks of Earth would have been dry, rocky planetesimals. Water that currently exists on Earth must have been delivered later, after the planet had largely formed and cooled somewhat. Two main sources have been proposed: asteroids and comets. Asteroids, particularly those in the outer main belt, contain water bound in minerals as hydrated silicates. When these asteroids collided with Earth, they delivered water along with rock. Meteorite samples from certain asteroid types show water contents of several percent by weight. Enough such material impacting Earth could account for the oceans. Comets offer an alternative or complementary source. They contain abundant water ice, and during the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system experienced intense impacts, many comets and asteroids struck Earth. Cometary impacts could have delivered substantial amounts of water. To distinguish between these sources, scientists compare isotopic ratios. Hydrogen has two stable isotopes, regular hydrogen and deuterium, which has an extra neutron. The ratio of deuterium to hydrogen, DH, varies depending on where and how water formed. This ratio is a fingerprint that can trace water sources. Earth's oceans have a DH ratio of about 156 parts per million. Water formed in the inner solar system, close to the Sun, tends to have a lower DH ratio. Water formed in the colder outer solar system tends to be enriched in deuterium, giving a higher DH ratio. By measuring the DH ratio in comets and asteroids, we can assess which is more likely to have delivered Earth's water. Early measurements of comets, including Halley's Comet, showed DH ratios roughly twice that of Earth's oceans. This suggested that comets were not the primary source. If comets delivered most of Earth's water, the oceans would have a higher DH ratio than observed. This favored asteroids as the main water source. However, more recent measurements have complicated the picture. Comet 103P Hartley 2, measured by the Herschel Space Observatory, showed a DH ratio matching Earth's oceans within uncertainties. This was surprising and suggested that not all comets are enriched in deuterium. Perhaps comets formed in different regions of the outer solar system have different DH ratios depending on local conditions during formation. Rosetta measured the DH ratio in Comet 67P and found it to be 3 times higher than Earth's oceans. This again suggested that comets like 67P did not contribute significantly to Earth's water. But this might mean that only certain types of comets, perhaps those formed in specific locations, have the right isotopic composition to match Earth. The picture that's emerging is complex. Earth's water likely came from multiple sources. Asteroids probably contributed, delivering water bound in minerals. Some comets, particularly those formed in regions where the DH ratio matched Earth's conditions, might also have contributed. The exact proportions remain uncertain. Another line of evidence comes from the abundances of noble gases. Xenon, a heavy noble gas, shows isotopic anomalies on Earth that might be explained by cometary contributions. Comets contain noble gases trapped in their ices. If comets delivered a significant fraction of Earth's water, they would also have delivered noble gases with specific isotopic signatures. Comparing these signatures helps constrain the cometary contribution. The timing of water delivery matters too. If Earth received its water very early, during the main phase of accretion, water would have been mixed throughout the planet and possibly lost due to high temperatures and impacts. If water arrived late, after Earth had largely formed and cooled, it would have stayed on the surface. The late veneer hypothesis suggests that a final veneer of material, roughly 1% of Earth's mass, was added after core formation. This late veneer could have brought water and volatile elements like carbon and nitrogen. Comets might also have delivered organic molecules. We know comets contain a rich inventory of organics, including amino acids. If comets struck Earth during or after the period when life originated, they could have provided chemical feedstock for prebiotic chemistry. This doesn't mean life came from comets, but comets might have supplied some of the ingredients. Mars provides a comparative case. Mars is smaller than Earth and has less gravity, making it easier for impacts to deliver material. Isotopic measurements of Martian meteorites suggest Mars received water with a different DH ratio than Earth. This might indicate different sources or different timing of delivery. Understanding where Mars's water came from helps constrain models of water delivery throughout the inner solar system. The contribution of comets to Earth's water remains an active research area. It seems unlikely that comets alone provided all the water. Asteroids probably played a significant role. But comets might have contributed a fraction, perhaps 10% to 30% of the total, especially if certain comets had favorable isotopic ratios. As we study more comets and measure their compositions more precisely, the picture will clarify. This question connects directly to the search for life beyond Earth. If water delivery via comets and asteroids is a common process, then rocky planets in other star systems might also receive water this way. This increases the likelihood that habitable conditions, liquid water on a surface, exist elsewhere. Understanding our own origins informs our expectations for what we might find around other stars. Comets are not eternal. Each passage through the inner solar system takes a toll, removing mass and gradually depleting the volatile ices. Over time, comets evolve, their activity decreases, and eventually they reach an end state. Understanding what happens to comets over long timescales reveals much about their nature and the dynamics of the solar system. A comet falling in from the Oort cloud for the first time is pristine, largely unaltered since the solar system's formation. Its surface might have been slightly processed by cosmic rays and impacts, but the interior remains frozen and unchanged. When this comet approaches the Sun and heats, volatile ices sublimate vigorously. The comet develops a large coma and prominent tails. Gas and dust production rates are high because the nucleus contains abundant fresh ices. On subsequent passages, if the comet's orbit brings it back, the comet is less active. Some of the most volatile ices, carbon monoxide and carbon dioxide, might be depleted from the outermost layers. A dust mantle might form, covering parts of the surface and insulating the ice beneath. The comet is still active, but less so than on its first visit. Short-period comets, those with orbital periods of less than 200 years, return frequently. Each return removes more mass. After hundreds or thousands of orbits, the comet's ices become depleted. Eventually, the comet no longer produces enough gas to create a visible coma or tail. It becomes dormant, appearing like an asteroid. Some observed asteroids might be dormant or extinct comets. Objects with asteroid-like appearances but comet-like orbits suggest this scenario. 3200 Phaethon, for example, orbits with characteristics typical of a comet and is the source of the Geminid meteor shower, usually associated with cometary dust. Yet Phaethon shows no cometary activity. It might be a comet that has exhausted its volatile ices, leaving only the rocky dust component. Comets can also disintegrate. The forces acting on a nucleus are substantial. Solar heating creates thermal stresses. Rotation generates centrifugal forces. Tidal forces from the sun or planets can stress the nucleus. Because cometary nuclei are weak and porous, these forces can cause them to break apart. Comet Shoemaker Levy 9, captured by Jupiter and then torn apart by tidal forces, is an extreme example. When the comet passed within Jupiter's Roche limit, the distance where tidal forces exceed the body's self-gravity, it fragmented into more than 20 pieces. Similar processes can occur near the Sun. Comets passing very close to the Sun, called sun grazers, often don't survive. They either evaporate completely or break apart under thermal and tidal stresses. The Kreutz family of comets comprises hundreds of objects, mostly discovered by space-based solar observatories, that follow similar orbits and pass extremely close to the Sun. These comets are probably fragments of a much larger progenitor comet that broke apart centuries or millennia ago. Each fragment follows a similar orbit, and when they approach the Sun, many evaporate completely, creating brief flashes of light before vanishing. Outbursts, sudden increases in activity, can also disrupt comets. If gas pressure builds beneath a thick dust mantle and then breaks through suddenly, the resulting outburst can fracture the nucleus. Comet 73P Schwassmann. Wachmann 3 broke into multiple pieces during its 1995 apparition. When it returned in 2006, observers saw dozens of fragments, some producing their own comets and tails. The fragments gradually separated, each following slightly different orbits. The end states for comets vary. Some become dormant asteroids, their volatile ices exhausted but their rocky cores intact. Some disintegrate entirely, leaving only meteor streams marking their former orbits. A few might collide with planets or the Sun, ending in dramatic impacts. Most simply fade away, becoming too faint to observe as they recede into the outer solar system or drift into interstellar space. Long-period comets that are ejected from the solar system by gravitational interactions with planets might wander interstellar space forever. Once a comet is moving faster than the Sun's escape velocity, it will never return. It becomes an interstellar object, drifting through the galaxy, until perhaps, millions of years later, it encounters another star system. The discovery of interstellar objects passing through our solar system, like Oumuamua in 2017 and Comet Borisov in 2019, suggests that such ejected comets are common. Every planetary system probably ejects comets during its formation. These objects then travel between stars, occasionally passing through other systems. The galaxy might be filled with interstellar comets, far outnumbering the comets bound to any particular star. The lifetime of a short-period comet is limited. Estimates suggest that a typical comet loses roughly 0.1% to 1% of its mass each time it passes perihelion. After a few thousand orbits, the volatile ices would be exhausted. For a comet with a 10-year period, this means a lifetime of tens of thousands of years as an active comet. For comparison, the solar system is 4.5 billion years old. Short-period comets we see today can't have been on their current orbits for the entire age of the solar system. They must be recently arrived from the Kuiper belt or scattered disk. This implies a resupply mechanism. The Kuiper belt and scattered disk contain vast populations of icy bodies. Gravitational perturbations gradually feed these objects into the inner solar system, replenishing the population of short-period comets. Without this resupply, short-period comets would have disappeared long ago. Long-period comets from the Oort cloud have different dynamics. They might make only one passage through the inner solar system in their entire existence. Their orbits are so long, thousands or millions of years, that they won't return within human timescales. Some might be perturbed during their passage, their orbits altered by planetary encounters, sending them into different trajectories or ejecting them from the solar system entirely. The fate of individual comets is stochastic, determined by chance encounters and unpredictable events. But statistically, the population's behavior is predictable. Comets are born in the outer solar system, wait for billions of years, occasionally fall inward, briefly shine as they pass near the sun, and then either return to the cold outer regions, are destroyed, or are ejected. The cycle continues, with new comets replacing those that are lost, maintaining a steady population of visible comets over long timescales. The most profound aspect of comets is what they preserve. Frozen at temperatures just a few degrees above absolute zero for billions of years, cometary ices retain information about the chemistry and conditions of the early solar system. Studying comets is like reading an archive, a chemical and physical record of a time when the sun was young and planets were still forming. When the solar system formed 4.5 billion years ago, the protoplanetary disk contained a mixture of gases and dust. The composition of this material reflected the chemical abundances in the interstellar cloud from which the solar system collapsed. Most of the mass was hydrogen and helium, but roughly 2% was heavier elements: carbon, nitrogen, oxygen, silicon, iron, and traces of everything else. As the disk cooled, different materials condensed at different temperatures and distances from the sun. Close to the sun, only the most refractory materials, those with the highest melting and vaporization temperatures, could condense. These included metals and silicate minerals. Farther out, more volatile compounds could condense, including water ice, carbon dioxide ice, and methane ice. The material that condensed in the outer solar system, beyond the frost line, is what comets are made from. This material contains a detailed record of the conditions in that region. The isotopic ratios, the relative abundances of different elements, the types of organic molecules present, all encode information about the temperature, pressure, radiation environment, and chemical processes operating 4.5 billion years ago. One key insight from cometary studies is the presence of high-temperature minerals mixed with low-temperature ices. Silicate grains like olivine and pyroxene, which form at temperatures above 1000 degrees Kelvin, are found in comets. These grains must have condensed close to the sun, where temperatures were high, and then been transported outward, mixing with ices that condensed in the cold outer regions. This mixing implies that material circulated throughout the protoplanetary disk, driven by turbulence, gas flows, and possibly magnetic fields. The organic molecules in comets are equally informative. Comets contain simple organics like methane and ethane, more complex molecules like formaldehyde and methanol, and even amino acids, which are building blocks of proteins. The presence of amino acids in comets suggests that the chemical precursors to life were widespread in the early solar system and might have been delivered to Earth by cometary impacts. Some organic molecules in comets might have formed in interstellar space before the solar system existed. Cold molecular clouds contain complex organic chemistry, with molecules forming on the surfaces of dust grains. When the solar nebula collapsed from such a cloud, these pre-existing organics were incorporated into comets. Detecting such molecules provides a direct link between interstellar chemistry and the chemistry of planetary systems. Isotopic ratios offer another window into cometary origins. Different isotopic ratios arise from different formation processes and environments. For example, the oxygen isotopic composition of water in comets can reveal whether that water formed from gas phase reactions or from ice grain surface reactions. The DH ratio we discussed earlier tells us about the temperature at which water formed. Measurements of noble gases in comets, like xenon and krypton, provide constraints on the temperature and pressure during formation. Noble gases are chemically inert and don't react with other elements, but they can be trapped in ices. The abundances and isotopic ratios of noble gases encode information about the conditions when the ices formed and froze. Studying comets also informs us about processes that operated in the early solar system but are no longer active. The protoplanetary disk existed for only a few million years before most of the gas was either accreted into planets or dispersed by the young sun's radiation and stellar wind. Comets formed during this brief window and have preserved a snapshot of that era. The diversity among comets, the variations in composition, activity, and structure, tells us that the outer solar system wasn't uniform. Different regions had different temperatures, pressures, and compositions. This heterogeneity reflects the complexity of the protoplanetary disk, with local variations in conditions affecting what condensed where. Some comets might even contain pre-solar grains, tiny particles that formed around other stars before our solar system existed. These grains have been found in meteorites, identifiable by their highly anomalous isotopic compositions that don't match anything formed in our solar system. If found in comets, pre-solar grains would directly demonstrate that comets preserve material older than the Sun itself. By analyzing cometary material returned by spacecraft, or by studying comets remotely, we can test models of solar system formation. Do the observed abundances match predictions? Are there unexpected elements or molecules that challenge our understanding? Each measurement refines the story. Comets bridge the gap between interstellar chemistry and planetary chemistry. They connect the cold molecular clouds where stars form to the rocky planets where life might arise. Understanding comets means understanding the chemical journey from diffuse interstellar gas to the complex chemistry that makes planets and, potentially, life possible. As you settle deeper into this exploration, consider the extraordinary idea that comets are messengers carrying information across billions of years. A comet passing through the inner solar system today contains ices and organics that formed when the solar system was newborn. Studying that comet is like reading a message written in the chemical language of the early solar system, preserved in ice and delivered across the vast distances and timescales of cosmic evolution. Comets are not just objects of beauty and scientific interest. They can also be harbingers of destruction. Throughout Earth's history, comets and asteroids have struck our planet, sometimes with catastrophic consequences. Understanding the impact hazard from comets is part of understanding our planet's past and assessing future risks. The late heavy bombardment, which occurred roughly 4 billion years ago, was a period of intense impacts. The inner solar system experienced a surge in collisions from comets and asteroids. This bombardment might have been triggered by orbital migration of the giant planets, particularly Jupiter and Saturn, whose gravitational influence scattered objects from the outer solar system inward. Earth, along with the Moon and other terrestrial planets, was heavily cratered during this time. Large impacts can have profound effects. An impactor several kilometers across hitting Earth releases energy equivalent to millions or billions of nuclear weapons. The immediate effects include shock waves, intense heat, and crater formation. A 10-kilometer asteroid or comet, traveling at tens of kilometers per second, would excavate a crater over 100 kilometers wide. The ejector, material blasted into the atmosphere and beyond, would rain back down, heating the atmosphere and potentially igniting fires globally. The long-term effects are equally severe. Dust and aerosols lofted into the stratosphere would block sunlight, causing a dramatic drop in temperature. This impact winter could last for years, disrupting photosynthesis and collapsing food chains. If the impact occurred in the ocean, it would generate mega tsunamis that would inundate coastlines thousands of kilometers away. The most famous example is the Chicxulub impact 66 million years ago, which led to the extinction of the dinosaurs. A 10-kilometer asteroid, or possibly a comet, struck what is now the Yucatan Peninsula, creating a 180-kilometer wide crater. The impact released energy equivalent to billions of nuclear bombs. The ensuing environmental catastrophe caused the extinction of roughly 75% of Earth's species, including all non-avian dinosaurs. The evidence for this impact is overwhelming. The Chicxulub crater has been identified and dated precisely. A layer of sediment found worldwide, dating to 66 million years ago, contains high concentrations of iridium, an element rare in Earth's crust, but common in asteroids and comets. This iridium layer marks the boundary between the Cretaceous and Paleogene periods, the KPG boundary. Fossils below this layer include dinosaurs. Fossils above it don't. Other mass extinctions in Earth's history might also be linked to impacts. The Permian-Triassic extinction 252 million years ago, the worst mass extinction known, killed roughly 96% of marine species and 70% of terrestrial vertebrates. While the primary cause seems to be massive volcanic eruptions, some evidence suggests impacts might have contributed. Smaller impacts occur more frequently. The Tunguska event in 1908 involved an object, probably a small asteroid or comet, exploding in the atmosphere over Siberia. The explosion flattened 2,000 square kilometers of forest but left no crater. The object likely disintegrated in the air, releasing energy equivalent to 10 to 15 megatons of TNT. If such an event occurred over a populated area, the consequences would be devastating. Comet impacts are potentially more dangerous than asteroid impacts for several reasons. Comets can approach from any direction, including steep angles to the ecliptic plane, giving less warning time. They move faster than asteroids because they fall in from the outer solar system. A long-period comet arriving from the Oort cloud might be detected only months before impact, too late to mount any deflection effort with current technology. Comets are also more fragile than asteroids. They could break apart in Earth's atmosphere, creating multiple impacts. Or they might break up before reaching Earth, creating a swarm of fragments that strike over a wider area. The effects could be spread out geographically, but still devastating. Current efforts to detect potentially hazardous objects focus on near-Earth asteroids. Surveys have catalogued most asteroids larger than 1 kilometer that cross Earth's orbit. The risk from these objects is now well characterized. But detecting long-period comets is more challenging. They spend most of their time in the outer solar system, where they're faint and invisible. Only when they approach the inner solar system do they brighten and become detectable. Improving our ability to detect and track long-period comets is essential for planetary defense. Advanced telescopes, particularly wide-field surveys that can monitor the entire sky regularly, help. Space-based observatories that can detect objects in infrared wavelengths, where even dark objects emit thermal radiation, offer advantages. If a hazardous comet were detected on a collision course with Earth, what could we do? Deflection is possible with sufficient warning time. Techniques include kinetic impactors, where a spacecraft slams into the comet to alter its velocity, or gravity tractors, where a spacecraft's gravitational pull gradually changes the comet's trajectory. Nuclear explosions, not to destroy the comet, but to ablate material from its surface, creating thrust, are another option. The key is early detection. With years or decades of warning, even small changes in the comet's velocity could be enough to make it miss Earth. With only months of warning, deflection becomes much harder or impossible. This underscores the importance of continuing and expanding efforts to survey the sky and track all potentially hazardous objects. Impacts are part of Earth's history. They've caused mass extinctions, but also delivered water and organic molecules that might have contributed to life's origins. The impact hazard remains, a reminder that Earth exists in a dynamic solar system where collisions still occur. Understanding comets, their orbits, their compositions, and how to detect and potentially deflect them is part of safeguarding our planet's future. Long before science explained comets, they captivated the human imagination. Appearing suddenly in the night sky with their glowing heads and streaming tails, comets seemed to defy natural order. They moved differently from stars and planets, following unpredictable paths. Ancient cultures worldwide observed comets and wove them into mythology, religion, and historical narratives. In ancient China, comets were recorded meticulously in astronomical records spanning thousands of years. Chinese astronomers classified comets by the shapes of their tails and considered them omens, signs that required interpretation by court astrologers. The appearance of a comet might signify the death of a ruler, the beginning of a dynasty, war, or disaster. These records, some of the oldest continuous astronomical observations in human history, provide valuable data. Modern astronomers use Chinese records to trace the historical appearances of comets like Halley's. In ancient Greece, comets were seen as atmospheric phenomena, not celestial. Aristotle believed comets were exhalations from Earth, vapors rising into the upper atmosphere and igniting. This view persisted in Europe for centuries. It wasn't until the 16th and 17th centuries that observations by Tycho Brahe and others demonstrated that comets were beyond Earth's atmosphere, moving through space among the planets. Medieval Europe viewed comets with dread. They were seen as harbingers of doom, signs from God warning of plague, war, or the apocalypse. The appearance of a bright comet often coincided by chance with significant historical events, reinforcing these beliefs. The Great Comet of 1066, visible during the Norman conquest of England, was famously depicted in the Bayeux Tapestry. King Harold's advisors interpreted it as a bad omen, and indeed, Harold died at the Battle of Hastings shortly afterward. Despite the fear, comets fascinated people. Their beauty, the sight of a glowing apparition with a long tail stretching across the sky, inspired awe. Artists depicted comets in paintings and tapestries. Writers included them in literature, using comets as symbols of change, fate, or divine intervention. The scientific revolution transformed understanding. When Edmund Halley predicted the return of his comet, and it appeared on schedule in 1758, it demonstrated that comets followed natural laws. They weren't supernatural omens, but physical objects with predictable orbits. This shift epitomized the Enlightenment's triumph of reason over superstition. Yet comets retained their power to inspire. Mark Twain was born during an appearance of Halley's comet in 1835. He famously predicted he would die when it returned, saying, "I came in with Halley's comet in 1835. It is coming again next year, and I expect to go out with it." Remarkably, he died in April 1910, just one day after Halley's comet made its closest approach to Earth. Whether coincidence or self-fulfilling prophecy, the story captures how comets continued to hold symbolic weight, even in the modern era. In the 20th century, comets remained subjects of fascination. Comet Hale-Bopp's appearance in 1997 was visible for months, delighting millions. But it also became associated with tragedy when the Heaven's Gate cult committed mass suicide, believing they would be transported to a spaceship trailing the comet. This dark episode reminds us that comets can still evoke powerful, sometimes irrational, responses. Science fiction has embraced comets as plot devices. From threats of impact requiring heroic efforts to avert catastrophe, to comets serving as transport for aliens or harboring life, comets appear across the genre. Arthur C. Clarke's novel, The Hammer of God, explores humanity's response to a comet on a collision course with Earth. Gregory Benford's Heart of the Comet imagines colonists living on Halley's Comet. These stories reflect our anxieties and hopes about comets. Comets also appear in popular culture more broadly. They symbolize fleeting beauty, rare events, or transformative change. A comet passing in the sky can mark a significant moment in a film or novel, a cosmic punctuation to human drama. The imagery of a comet, bright and transient, resonates deeply. The cultural legacy of comets reflects humanity's long relationship with the night sky. For most of history, people lived under dark skies, and celestial events were visible and significant. The appearance of a comet was a communal experience, observed by entire societies and remembered for generations. In our modern era, light pollution has dimmed the night sky for much of humanity. Few people see the Milky Way regularly, and fainter astronomical phenomena go unnoticed. Yet when a truly bright comet appears, it can still capture widespread attention. People venture outside, away from city lights, to witness the spectacle. In those moments, we connect with the same sense of wonder felt by ancient observers, a shared human experience spanning millennia. The comet becomes a reminder that we live in a vast, dynamic universe, one that occasionally presents us with beautiful and humbling sights. As you drift toward sleep, imagine standing under a dark sky, no city lights to wash out the stars, looking up at a brilliant comet. Its coma glows softly, a fuzzy ball of light. Its tail streams away, stretching across the heavens, pale and ethereal. Around it, the stars shine, unchanging, providing context and scale. You feel the immensity of space, the vast distances involved, the deep time represented by this frozen visitor falling toward the light. And you feel connected to generations of humans who stood, as you do now, gazing up in wonder. Our exploration of comets has only just begun. The missions launched so far have provided revolutionary insights, but many questions remain. Future missions will delve deeper, literally and figuratively, seeking to answer fundamental questions about comets and what they tell us about the solar system's origins. One priority is sample return. Stardust returned micrograms of dust particles from Comet Wild 2, but returning larger samples, including pristine ice from the nucleus interior, would provide far more information. A mission that could land on a comet, drill beneath the dust mantle, extract core samples including ice, and return them to Earth would be transformative. Analyzing those samples with laboratory instruments far more capable than anything that can be sent to space would reveal details about composition, isotopic ratios, organic complexity, and physical structure that remote observations can't provide. Designing such a mission poses challenges. Comets have very low gravity, making landing and anchoring difficult. The Rosetta mission's Philae lander bounced when it touched down, ending up in a shadowed location where it couldn't generate sufficient solar power. Future landers need better anchoring systems, perhaps harpoons or drills, to secure them to the surface. And operating in the extremely cold temperatures and potential outgassing environment near the nucleus requires robust engineering. Another goal is visiting multiple comets. Each comet is unique, and studying several would reveal the diversity within the cometary population. A mission that could visit several comets, measuring their compositions and structures, would help determine whether the differences observed represent distinct formation regions or processes. Are Kuiper Belt comets different from Oort cloud comets? Do different comets have different DH ratios, different organic inventories? Proposals exist for missions to target long-period comets, those making their first passage through the inner solar system from the Oort cloud. These comets are the most pristine, never having been heated by the sun before. A spacecraft intercepting such a comet would observe material unchanged since the solar system formed, the ultimate time capsule. Deep penetrators, projectiles that burrow into the nucleus and transmit data from beneath the surface, are another concept. Understanding the interior structure and composition of comets is crucial. Is the nucleus homogeneous or layered? How does temperature change with depth? What's the porosity? Penetrators could answer these questions, providing ground truth for models. Longer duration orbiters, following comets for multiple orbits, would track how comets evolve over time. Do they lose mass uniformly, or does activity change from one orbit to the next? How do surface features evolve? Long-term observations would capture these changes, offering insights into cometary aging. Utilizing comets as resources is another frontier. Comets contain water and organic materials valuable for sustaining human activities in space. A future where spacecraft or habitats harvest cometary ice for water, oxygen, and hydrogen fuel is conceivable. Comets orbiting in the inner solar system could become waypoints or resource depots. This isn't imminent, but as space exploration expands beyond low Earth orbit, utilizing in situ resources becomes increasingly important, and comets represent accessible resources. Defending Earth from cometary impacts requires better detection and tracking. Expanding ground-based and space-based survey capabilities to detect long-period comets earlier would provide more warning time. Developing and testing deflection technologies, including kinetic impactors and other methods, ensures readiness. The DART mission, which successfully altered the orbit of the asteroid Dimorphos in 2022, demonstrated that kinetic impactors can work. Applying similar techniques to comets, which are more fragile, would require testing and refinement. International collaboration will be key. Comet missions are expensive and complex, often benefiting from shared costs and expertise. ESA's Rosetta mission, NASA's Stardust, and JAXA's potential future contributions exemplify how agencies can work together. Combining observational data from different missions, coordinating sample analyses, and sharing findings accelerates progress. Amateur astronomers continue to play a role. Many comets are discovered by amateurs, and their observations contribute to understanding cometary behavior. Citizen science projects engage the public in analyzing comet images, tracking activity, and monitoring changes. This democratization of astronomy, where anyone with a telescope can contribute, enriches the scientific endeavor and maintains public interest. Education and outreach are vital. Comets naturally captivate people, making them excellent tools for teaching astronomy, planetary science, and the scientific method. When a bright comet appears, it offers a teachable moment, a chance to explain orbits, solar system structure, and the processes shaping celestial objects. Future missions will continue this tradition, inspiring the next generation of scientists and engineers. The philosophical implications of comet studies extend beyond science. Comets remind us of our connection to the cosmos. They delivered water and organics that made life possible. They inspired generations of stargazers. They connect us to the deep past, carrying material older than Earth itself. Understanding comets is part of understanding ourselves, our origins, and our place in the universe. As missions venture farther, target more comets, and return more samples, our knowledge will deepen. Each discovery raises new questions, propelling exploration forward. The future of comet exploration is bright, promising answers to long-standing mysteries and revelations we haven't yet imagined. Here on Whispering Universes, we celebrate this journey, the patient work of scientists and engineers extending humanity's reach into the cosmos, one mission at a time, one comet at a time, gradually assembling a comprehensive picture of these frozen travelers and what they reveal about the universe's workings. As you drift toward the edge of sleep, let your thoughts turn once more to comets, those silent wanderers moving through the dark. Consider what they represent. Time made tangible, frozen into ice and stone, preserved across billions of years. Every comet is a traveler not just through space but through time, carrying within its frozen heart the chemical signature of an era long before Earth's continents formed, before life colonized the land, before any creature looked up at the night sky and wondered what those points of light might be. Time, for a comet, is different than for us. We measure our lives in years and decades, feeling time's relentless passage in every moment. A comet's existence spans epochs, 4.5 billion years sitting motionless in the Oort cloud, silent and dark, neither aging nor changing in any meaningful way. Then a gravitational nudge sends it falling toward the sun, a journey that might take hundreds of thousands of years. Even moving, even approaching the light, the comet remains mostly unchanged until that final plunge into the inner solar system, where solar heat finally wakes it from its ancient slumber. In those weeks or months near the sun, the comet's entire existence transforms. Ices sublimate, gases stream away, dust is released. The comet blazes across our sky, magnificent and doomed, losing mass with every moment. And then, if it survives, it recedes back into the dark, returning to the cold outer regions where it might wait another 10,000 years or 10 million before falling inward again.